Welcome to my channel Maithili SK. In this session, I am going to explain you about vestigial sideband modulation and the generations of the same. So we are going to cover in this class why we go for vestigial sideband amplitude modulation, its mathematical representation, generation and deduction of the same. So actually why we go for SSB SE modulation is explained in the previous topics. So we know the three components of amplitude modulated signal, that is carrier, upper sideband and lower sideband. So when last point what we have seen is what happened when one of the carrier is being suppressed, we obtain DSB SE AM. And next case, when we suppress one of the sideband and as well as the carrier, we get single sideband suppressed carrier AM. So this is the way we have obtained with respect to SSB SE AM. Now coming to VSB SE AM. So to avoid this loss which is happening due to the sideband suppression frequency component, we can compromise between this double sideband and single sideband suppressed carrier AM. So actually we know for a single sideband suppressed carrier AM and a double sideband suppressed carrier AM, we have a carrier is being suppressed and we have either a single sideband with respect to upper sideband or lower sideband. So if it is an upper sideband or lower sideband, we can say only one of the sideband component is present here. So we theoretically we can get only one of the sideband component by means of using an ideal bandpass filter. But practically we cannot get this entire sideband frequency component due to information gets lost. So to avoid this loss technique, we are going to compromise between these two advantages, that is with respect to DSB-SE as well as with the respect to SSB-SE. So what is SS, double sideband is nothing but we have both the sidebands. What about single sideband is we have one of the sidebands. So if we are compromising between these two means what is it nothing but we will be having one sideband fully, whereas one of the sideband present in the single sideband will be partially suppressed. That is what is called as vestigial sideband. So what is the meaning for vestige is nothing but a part from which the name has arrived. So vestige is nothing but simply a part. So a portion from a single sideband is being taken for the transmission. So it is called as vestigial sideband. So now coming to the spectrum component part, it will be easier if you could understand with respect to spectra of the vestigial sideband AM. So this is what the spectrum here is. So if I am taking this dark color as the upper sideband, so here a part of this lower sideband is being transmitted. So not fully the lower sideband is concentrated, only the part of this lower sideband is concentrated. So it is called as a vestigial sideband. So here this application is widely used in television systems. So you know a TV system is consisting of an audio as well as a video signal. So if you are imagining this as a two signal component, audio as one of the signal component, video as one of the signal component, this requires a full sideband to be carried means only a part of the sideband is required for the another format or the message signal. Hence this is mostly widely used in TVs or transmission of television signals. So this is the plot we can actually get for the vestigial sideband. So as I said, from the lower sideband, this lower sideband part is completely suppressed and only this part and this part is being carried over for transmission. So it is called as vestigial sideband. So please do remember that. So what will be the bandwidth for this vestigial sideband? So you could see here a part of the message signal which is transmitted. You could see here from here this till it will be FM, whereas here to this signal it is not fully there FM minus FM, but it is a vestigial sideband. So it is a vestigial frequency FV. So I am getting a bandwidth which is nothing but equal to FM plus FV. Now coming to the advantages part of a vestigial sideband AC AM, it is highly efficient. It reduces bandwidth when compared to AM and DSB waves, and filter design is easy, and transmission of low frequency component is possible without any difficulty, and it possesses good phase characteristics. What are the disadvantages of vestigial sideband SEAM includes bandwidth is more complex because you have to send only a partial of the signal. So bandwidth is more complex when compared to SSB SEAM because it is not precisely cut at the same where it is vestige. And demodulation part is very complex in vestigial sideband. Coming to the application, as I said, it is widely used in TV signals. Now coming to the mathematical representation of vestigial sideband AM, let us consider a message signal of two sinusoids. So I am taking here a message signal component with two sinusoids, that is I am considering here the cosine waveform. So it is Vm of t is taken as V1 cos omega mt and V2 cos omega 2t. Now, assuming vestigial sideband is used for modulating TV signal, it contains audio as well as video signal. So, this can be represented as two sinusoids again. Hence, the message signal is then multiplied by the carrier, which is nothing but cos omega ct, to form the double sideband signal. So, we are just what is double sideband is nothing but we will be just multiplying message signal with respect to carrier signal. So here the message signal is Vm cos omega mt. Cos omega mt, there is only cos omega 1t plus V2 cos omega 2t into carrier signal is cos omega ct. So just solving this same, we will be getting by using trigonometric solution as cos A cos B, which is nothing but half of that is we get one upper sideband and lower sideband with respect to the frequency component. So now this can be simply rewritten as V DSB as V1 of 2 into cos omega C plus omega 1 of t plus cos of omega C minus omega 1 of t plus V2 by 2 into cos of omega C plus omega 2 into t, because we are considering here two terms of omega 1 and omega C term with respect to omega terms. So with respect to carrier, it gets solved here, and the spectrum for this is shown as a single-sided band. RH is only spectrum. That is, the spectrum for this is shown here, and the VSB filter is then used to generate the VSB signal. So we can say here when it is passed through the VSB filter, the filter eliminates the unwanted signal, and we will be getting only the skirts of the signal which is to be transmitted. The skirt of the VSB filter must be symmetrical about the carrier. So here symmetrical in the sense it should be equivalent with respect to left and right side. So now the output of the double sideband waveform AM is passed through the low pass filter having the frequency response as shown below. So when it is passed, so it will be eliminating the unwanted signals. So you will be getting three terms, that is a vestige part of a lower sideband and a upper sideband with respect to the same. So you will be getting vestigial VSB of T. This is the output message signal of a vestigial sideband modulated signal, which contains 1 by 2 V1 of epsilon cos of omega C minus omega 1 into T plus 1 by 2 into V1 of 1 minus epsilon into cos of omega C plus omega 1 into T plus V2 by 2 into cos of omega C plus omega 2 into T. So this is the above equation representing the mathematical equation of vestigial sideband AM. Now coming to the generator part of the vestigial sideband. So VSB generation is similar to that of a single sideband suppressed carrier AM generation. So we'll be having simply a generator as well as a demodulator of the same. Now coming to the VSB generator. In this method, first we will generate a DSB SE wave with the help of a product modulator. Then we will be applying the DSB wave as an input to the shape that is band pass filter. Then this filter produces an output which will be a vestigial sideband output wave. Then selecting the frequency range of the band pass filter as a spectrum of the desired SSB SE wave, we will be getting a VSB generator output. So this is the simple sketch of a VSB generator where we will be passing a message signal M of t and a local oscillator generator carrier signal to the product modulator. This product modulator just multiply these two signals M of t into C of t to produce a double sideband suppressed carrier wave. Then it is passed to the sideband shaping filter, which finally suppresses one of the sidebands, either lower sideband or upper sideband, and gives a vestigial sideband output. Coming to the form, how it is obtained mathematically, we will be seeing here the message signal and the carrier signal which is applied here is given to the product modulator. So the product modulator output is considered as P of t, means it is nothing but this is the carrier signal code and this is the message signal M of t. So generally applying the Fourier transform on both the sides, because we are going to consider in terms of frequency representation. Here applying Fourier transform, this P of t becomes P of f into AC by 2 into considering this term message signal M of f minus fc plus M of f plus fc. So upper sideband and lower sideband is being generated. The above equation represents the DSB-SC frequency spectrum with respect to frequency, and the transfer function of the side shaping filter will be represented as H of f. So we are passing this double sideband output to the sideband shaping filter. So the sideband shaping filter produces a single vestigial sideband output. So the first filter has the input of P of t and the output is a vestigial sideband output, which is nothing but S of t. So that S of t is also here represented as S of f in Fourier transformation. So S of f is nothing but P of f into H of f. So we know H of s is a impulse function. That is a function which is given to the transfer function of the filter. So S of f is equal to P of f into H of f. Now substituting P of f from the above equation which is solved above. So we will be getting AC by 2 into M of f minus fc plus M of f plus fc into H of f. So this above equation represents a vestigial sideband spectrum in terms of frequency component. So now coming to the demodulation part of the vestigial sideband, as I have earlierly mentioned, this VSB SC detection is somewhat critical, difficult or complex in terms. So we will be seeing here step by step. So demodulation of vestigial sideband wave is similar to the demodulation of SSB SEAM. So in SSB SEAM we have seen with respect to coherent reduction. Here also we will be using a coherent or a synchronous reduction of the same. So the VSB demodulator figure is shown in the figure below. So you could see here the output obtained from the VSB SC wave is given as an input to the product modulator, and a local oscillator generated carrier signal is passed to the signal here, and finally the obtained output of a product modulator V of t is given to the low pass filter to give a demodulator or the message signal output which we have passed. So in this process, the message signal can be extracted from the VSB wave by multiplying its carrier with multiplying it with the carrier. That is, the VSB SC wave is just multiplied with respect to carrier to produce a V of t signal. That is what explained here. The resulting signal is passed through the low pass filter. This is the low pass filter, and the output of the filter is the desired message signal. That is the demodulated signal actually. So let a VSB SC wave represented by S of t and the carrier signal be represented by AC into cos omega ct or 2 pi fct. From the figure we can write the output V of t as nothing but S of t into this carrier signal S of t, that is AC cos omega ct. So applying Fourier transform on both sides, we will be getting this instead of V of t, t is represented in frequency domain V of f, AC by 2 into S of f minus fc. We are getting in terms of upper sideband and lower sideband with respect to frequency component. We know with respect to S of f from the previous equation, it is AC by 2 into M of f minus fc plus M of f plus fc into H of f. Now substituting that is, we can find the above from the above equation. We will be finding both the signals with respect to S of f minus fc and S of f plus fc. So what is S of f minus fc is nothing but here we have given the signal in terms of S of f. So what will be S of f minus fc? Instead of f, we are going to substitute f minus fc here and finding or representing the equation and solving the same. So similarly for this S of f, we are going to substitute S of f plus fc, and here for f we are going to substitute f plus fc the same. So on solving it, we will be getting these two terms of in terms of minus f minus 2fc and the f plus 2fc. So substituting this S of f plus fc and f minus fc in V of f, we will be getting two terms of functionality in terms of M of f minus fc. This these two equations are substituted here. So we'll be getting this equation with respect to V of f. So V of f finally, if it is solved, we'll be getting AC square before with respect to m of f. We are taking it outside. All these terms in terms of h of f is rewritten. So in the above equation, the first term represents the scaled version of the desired message signal. That is, we want only the message signal frequency, and the other things are the this scaled version of the signal spectrum. So it can be, what we want is only the message signal. So what we are going to do here is passing this signal through the filter. We will be surpassing all these unwanted signals and getting only the message signal component. Hence, after passing it through the low pass filter, we will be getting an output signal, which is nothing but the desired component of an upper sideband with a suppressed lower sideband. Hence, this is about the vestigial sideband suppressed carrier AM demodulation part. So, hope you understood with today's topic. It's a very simple topic and a very important topic as far as university question is concerned. Hope you understood. In next class, we'll be seeing about angle modulation. That is nothing but introduction to two types of modulation with respect to angle, that is frequency and phase modulation. Thank you.